Now you should see it.
Okay.
Yes.
You can start,
Great.
please.
Thank you. Sorry for the delay. Thanks for the invitation. My talk is about incorporating half-valves using varying permeability approach, which is joint work with my colleagues at the Medical University of Graz, a group of Professor Planck, and other colleagues in the group of Professor Steve Nieder at King's College in London. So I want to start. We have seen already quite some videos about hearts, and I'm a bit in the business of doing hemodynamics. So basically this is, you have seen already that simulating like a heartbeat. This is basically the result of what comes out during my slides. So I started like a bit with eye candy in the beginning. And this is basically from a patient specific case that we got from KCL in London. So this brings me to the contents of my talk. It's like, first I would like to tell you how we made this heartbeat. The second, which is maybe more interesting since we have seen already a few simulations, is if we have a model, how do we study like the sensitivities of these models, like sensitivities of input parameters to output parameters. And for this, we've come up using Gaussian processes and some surrogate models, and let's dive into it. So how did we do this model? So most of you know, basically you start from some kind of segmentation, you get some patient specific data, you segment it. In this case, it was done with Slicer. And then you get, we get basically a tagged segmentation, which we can put into a mesh software. In this case, it was Seagull, and then some other tools, post-processing. And the idea was, how much can we simplify the function of the valve to still be able to recover some useful results that are also interesting for clinical use. So what you see here is what we basically have the valves down in the subpicture E. You see these are basically just some kind of thicker planes that basically describe the location between tag regions, and this is what we use for how we describe the valves. Similar to what you saw before in the talks, the resistive surfaces, but we use basically resistive volumes. And with state-of-the-art tools that colleagues in KCL did, we also want to use as much data as we can get out of a patient scan. So in this case, there is a good knowledge at the lab of Professor Niederer how to basically match movement that you can generate from CT data, which you see here, with the motion of a mesh. So what we did is we made the mesh, and then basically we extracted the displacement of this domain out of CT scans in an optimized way. And this serves basically as the input then for the CFD. What's behind CFD, you know, and we basically think of the valves similar as this resistive surface method. We think of it as kind of obstacle that we want to penalize away, so we don't need to somehow, or similar to inverse boundary method. So we basically just also add a penalization term. Like if you think of it, it's like a Darcy drag term. And basically, wherever the penalty is huge, this thing will behave like a solid structure, and wherever the penalization is low, it will behave like a fluid. And then the question is, how do you determine this behavior? Of course, we need some boundary conditions. As you saw, we have some 0D Windkessel models where we estimate the parameters from some ad hoc measurements from clinical data. And on the rest of the surfaces, we use basically the motion as input to an Navier-Stokes ALE method. And on the outlets, for example, in this case, on the atria, we use fixed prescribed outlet pressures. In this case, for the simulation you saw before, it was 10 millimeters of mercury. Same thing holds for the right side of the heart. So what about these valves I mentioned briefly? What we use is basically we calculate the fractional volume map. So we have the surface description of this valve, and basically calculate what's inside, what's outside, and then assign a fractional volume to the elements in the mesh. This can be done in a very fast and efficient way. We have we provide a shared memory parallelized version of this for free, included in our toolbox mesh tool, where you can try that out if you want. This also can deal with motion and all these things. It's based on KD trees and some ideas from ray tracing. And basically, we just calculate this fractional volume map on the fly, and then this penalization parameter, it's just we fetch a kappa, which is a high value like this R that we saw in the slides of Ivan before, times this permeability or fractional volume map, and times some switching function that we infer from the data that we get from the clinic. What do I mean by that is if you have the motion extracted from your data set and you apply basically displacements, then you can calculate like volume transients of the compartments from the left ventricle, the right ventricle, then the atrium. And then you can just calculate flux transients by just taking the time derivative. And then basically wherever this time derivative is 0, we assume here is basically where the valve opens or closes. And since we had in these measurements, they are usually, you don't get a lot of time slices. So we had to work here, for example, with 10 time frames for covering a whole heartbeat. So there's also no like isovolumetric phase. So we have to interpolate in between. And that's why we also included here basically, instead of binary switching these resistive surfaces on and off, we just included a fudge factor here. There's like a duration period. And this is basically this phi. This goes from 0 to 1 and activates the obstacle or not. This looks then like that. So as I said, it's a very simple model of what the valve does. So we didn't care about the dynamics of the valve. So we didn't care about how the valve moves. We cared about the function of the valve, meaning impeding flow from one compartment to the other. And see, can we still extract some useful information with such a simple model? And you see here how these valves here switch. These are basically thresholds of this volumetric map. Okay, putting that all together, as I said, to discretize this Navier-Stokes equation, we use, we saw already in the talk from Professor Kenji Takizawa, we use basically also a variation multiscale method. And in time, we use the Janast alpha integrator. This produces a highly nonlinear system that we need to linearize. We try also to use every trick in the book to make the Newton become faster. So we use a quasi inexact Newton-Raphson method with Jacobi freezing and some other tricks to make the system, to make the assembly time of our solver less. And basically, we have a bit of a knowledge in HPC. So the software I'm using here is Carpentry, developed mostly from Medical University of Graz from Professor Gernot Planck and his group. And what you saw here, the simulation in the beginning, these are basically two separate simulations. Since we have extracted the motion, the blood pools themselves are geometrically separate, so we can do two separate simulations. For the left heart, since there's more flow dynamics there, we use basically a finer mesh with around 18 million finite elements. And for the right side, we use 6 million finite elements. These mesh resolutions were judged by a mesh convergence study based on Pope's criterion for resolved Elias simulations. And we simulated 4 heartbeats for each side of the heart at the VST4 cluster in Vienna at around 1,200 MPI processes. And this took us around 15 to 20 hours per heartbeat. And we used the final heartbeat then for extraction of some comparison values that you see here in this table below. And you see we have still that, though we use a really, really simplistic model of this valve, we still get some useful clinical results. So these delta P's, these are like mean gradient, mean pressure drops over the valve, and the Umax is basically the maximum velocity magnitude over the valve region. So this is like compared with clinical measurements to our simulation. Okay. So now that we made a heartbeat from this particular patient, the question is, how sensitive is our model? And this is where my second part of my talk is about the global sensitivity analysis using probabilistic surrogate models. So you have a CFD simulator, which basically you can think about. It's a hugely complicated nonlinear map from input data to output data. If you want to study how sensitive your simulator is to changes in the input parameters, how this affects output parameters, you have certain options. Like if you do global sensitivity analysis, you would need to vary, like do Latin hypercube sampling of your input parameter spaces, and then you would need to run tons and tons of CFD simulations. And so the natural idea is to replace this highly nonlinear input to solution map by something simpler. And this is, we replace it by probabilistic, fast evaluating surrogate model, also called Gaussian process emulation, which means we use a linear regression mean model and a zero mean Gaussian process. How do you basically, you train this GP by defining a suitable Latin hypercube sampling of your input parameter space, run a certain amount of CFD simulations. With that, you train your GP model, and then you can use this GP model instead of doing CFD simulations to draw as many samples as you want to do global sensitivity analysis. So what we did for our model, have a look at the time, we chose these parameters here that you see, basically the wind castle resistance, the left atrial pressure, then also these penalization parameters that we were interested in, whether the model idea of like penalizing these valves influences also the solution, and also these duration times. So we did basically 90 simulations per side of the heart for training the GP, and then basically we draw for the sensitivity analysis around 10,000 samples out of this GP to do the GSA lip, the GSA, which uses SA lip, and all of this together is summarized in a very, very recommendable software by my colleague Stefano Longobardi, a GPE that was also used in a talk the day before by my colleague Federica. And basically, these are the output values we compare, which are this is the left heart. We use some pressure differences, some kinetic energies, also residence times in certain compartments. What I mean by pressure differences, you see here with these bowls, these are basically temporal means over these bowls. And the residence times we calculate by a continuous approach, modeling basically convection diffusion equation for modeling the residence time, which we solve with the flux corrected transport algorithm. And summing up everything together, pulling everything with the GP, running the GP, doing the sensitivity analysis, you can then get this here as a result, which are heat maps summarizing the effects of your model from input to output. The interesting thing about this is that basically what was nice for us is that both of these penalization parameters do not really have a strong influence on the output of our model, which is good because to a certain extent it justifies using these penalized methods. And you see that basically parameters that are somehow coming from physics or some of them from something that makes sense clinically have strong influence on the output of our model. So basically the results told us that we are not that far off and we can still extract some meaningful results. And with that, hopefully in time, according to my timer here on my phone next to me. So basically I showed you we have like this pipeline for modeling a heartbeat using this resistive, this penalized valves. And it works. We still get some nice clinical validation out of that. And the GPE approach, so the surrogate modeling, is basically a very nice tool to study sensitivities of your model from input to output. And of course, limitation, I said before, it's a very small, there's no FSI involved here. This is basically a forward model and was meant as basically a proof of concept that this works and can be extended to other things. As we saw in a lot of talks during this conference, that there are a lot of building blocks to like making a whole heart simulator, and this might be one, and we would like to compare that to more sophisticated approaches and also compare it to more state-of-the-art FSI or IBM methods. And with that, I thank you for your attention, and I can highly recommend everyone to check out Stefano's software for starting your own journey in the Gaussian process world.
Thank you, Elias, for this very interesting talk. Questions from the audience? Cristobal, please.
Yeah. Hello, Elias. I have a question. I didn't. I don't know if I maybe I missed it, but so you have only the geometry of the valve, the closed configuration, or also do you have it in the open configuration in the?
No, it's that simplistic. It's basically just a thick plane that just basically cuts off the flow. So we basically have we segmented areas, so you might or might not see the valve in the CT scan, and we just said like, okay, here somewhere is the valve, and we draw basically a tag region in between there and use that, and basically with the switch function we just make it appear or disappear.
Okay, yeah.
But we also did I haven't brought that with me here, but we also modeled like the same thing with a more realistic valve. This we put in a paper that you can find on archive, where we tried that with a mock model, where we basically have 3 leaflets that also open, but this was like an artificially bioprosthetic valve that we inserted. But for this study, we basically really tried the most simplistic that we can think of.
Okay, but your CTs that you're showing are ECG triggered or not? It seems that yes, yeah, you have 10 phases. So,
excuse me, I didn't hear that. I didn't quite get that.
I have, I think, some connection problem. You have 10 phases in the CT, right? So you should be able to see the valve at the open position, I think.
Yeah. So let me just rephrase. If I understood, so I should see the valve in open position as CT scan in the 10 frames. You said that?
Yeah.
Yeah,
I have seen ECG gated, and yeah, you can segment even the valve.
Exactly. It just like it was deliberate in that sense that we made it as simplistic as possible.
Okay. Yeah. So which application do you have in mind for this, or do you have any? Or clinical?
Well, we were thinking of can we extend it further by, for example, having this in there and having pressure triggered opening and closing. So at the moment, I just we read out basically the opening and closing times from given data, but in other sense, we would like artificially measure the pressure before and after the valve, and then basically trigger an opening or closing. So
okay.
I could think of, but basically there are other people using it. We could also think of regurgitation modeling and things like that. So there are some things we could do. Yeah, but of course, it's if you're interested in the real dynamics of the valve, this is a different topic. So this was not the idea of what we did here.
No, I just was wondering if you may include, because of course, if you then have the shape at open position, then your flow also will change. It will just go through the valve.
Of course, the method is blind to how this shape looks like. I could also, if I have it in open and closed it, I could just interpolate between those states and then get basically this this movement.
Yeah. Okay. Okay, I think that I'm done with questions. Thanks.
Thanks for the question.
Okay, thank you, Cristobal. Sorry, Lorenzo, we have to stop here because time is over. So thank you, Elias, for your talk and answers. And the last speaker of today is Raidman Arostica from University of Groningen. So